Assalamualaikum warahmatullahi wabarakatuh. So in the previous video, we have already introduced you about flux and then reluctance, okay, and also what you call the magnetic force or MMF, okay, and actually this magnetic circuit where we have the magnetic force here, which is produced by winding up a material with a copper with a winding here, and then make sure that the current is flowing inside this coil, so it will produce the force. Okay, and this force will actually induce a flux inside these materials, but the amount of flux is actually depending on the flux flowing is actually depending on the reluctance, okay, or the flux value is depending on the reluctance of the material. So as you can see here, it is resembles the electrical circuit, okay. So to be a very simple approach is actually to get a circuit analogy of the circuit, so we can actually represent the magnetic force MMF as a voltage source, and the flux as the current, and the reluctance as the resistance. And you should know that F is equal to Ni, N is the number of turn, and the reluctance of the material is dependent on the length of the materials, okay, and mu over the mu and multiply with the cross section of the materials. And the MMF, as been mentioned earlier, is generated by the coil, okay, and the strength of the MMF depends on the number of turns and also the current, as been mentioned here, okay. And the units of the MMF is ampere turn. Okay, and furthermore, where we have already know that based on the circuit analogy, the flux, this can be obtained by using this equation, F over the reluctance of R, and since we already know F is Ni, so we can write down as this equation. Okay, so the longer the magnetic part, okay, L. So the longer of L, so the greater, or what we call the greater the value of the MMF is required to drive the flux, okay. And this magnetomotive force per unit length is known as the what we call the magnetizing force, which is defined as the symbol is H, and this H is equal to F over the L. Okay, so this represent the magnetizing force, okay, per unit length. And from H here, so we can actually derive another equation that relate between H and the flux density. So the relationship between the magnetizing force and flux can be write down as this one. So the B flux density is equal to the mu of the materials multiply with H, and you know that mu is mu O multiply mu R. Okay, so mu O is the permeability of the air space, and mu R is the relativity permeability, which is mu bagi mu over mu O, and this is has no unit because it's just a ratio, and the mu O, which is the permeability of the air, is actually 4 pi power of -7, and from your calculator you just can type constant 33, and mu R for the free space or for the air is unity, while for the other materials that can be magnetized, which is a ferromagnetic material such as iron, cobalt, and nickel, so the mu R can be either in several hundred and can be ranged from several hundred to several thousand. So the meaning of a large of mu R, meaning that if your mu r is large, meaning that you can produce a very large flux density with a very small current value. So even though from this relationship, B is equal to mu H, okay, it seems to be linear, okay, but actually this relationship of linearity is only applicable to a certain part only. So for example, this is B and this is H. So the relationship between B and H is linear at the several parts until some beyond the point, for example, this point, beyond this point, the relationship between B and H is no longer unity. So usually it will be actually a saturation, meaning that even though the magnetizing force is increased, the amount of density of flux is actually has a minimum increment. Okay. So this is actually several BH curve of different type of ferromagnetics. For example, we have the cast iron, steel casting, raw iron, and so on. Okay, so in practical, most of the BH resistance is not linear, and it's only linear to only a certain part. But after that, beyond that part, so usually the relationship is no longer linear. That's how sometimes in the calculation and to determine the B or H, so they will provide this graph, okay, for different type of ferromagnetic materials. For example, we can use this plot. For example, if B of the cast iron, if B is 0.6, okay, so 0.6 the intersection here, so meaning that when the flux density is 0.6, it will produce a magnetizing force of 3000, okay, 3000, and it's actually differ for different type of materials. So from this, what we can see that the highest, the best is actually a steel casting, because we need a very what we call minimum, okay, minimum magnetizing force to produce higher flux, okay, higher flux density. So steel casting is the best, and the worst is actually a cast iron. So actually in the electromagnetism theorem, so there are several rules that need to be followed and actually important in study the electromagnetics. So actually we have three. In this syllabus, we only concentrate on three, which is what we call the Ampere's law. The second one is the Faraday law, and the third one is the Lenz's law. So this is the Ampere law. So what is stated that actually suppose a conductor carries a current, so this current will actually produce what we call the magnetic field around the conductor. Okay, so if the current is increased, so the magnetic field is also will be increased. For the Faraday's law, it said that the magnitude of the induced EMF, so for example, this one is E, or voltage, okay, the induced voltage is actually directly proportional to the rate of change of the magnetic flux through a coil. For example, if you have like this, okay, if you have like this, so you have a coil that actually wind up here, okay, so and then you have what I call the permanent magnet, okay, where you actually go in and go out, okay, so it will produce what we call the voltage induced inside the solenoid. Okay, so the amount or the magnitude of the voltage, as can be seen here, is depends on the rate of change of the flux. So when you actually go in, okay, to this solenoid, okay, so it will change the magnetic flux. Okay, so if you actually do it in a very high speed, so the magnitude of the induced voltage will be very high. So that is the what they call the Faraday's law. Okay, the Lenz's law is actually complement the Faraday's law. Okay, it complements the Faraday's law, where in the Lenz's law it is said that it's just that the direction of the induced current that flow through the coil can be determined from the Lenz's law. So Lenz's law stated that the induced current always flow in the direction that opposes the change in the magnetic. So Lenz's law said that the voltage induced is actually negative, opposed of the change of the flux. Okay, and this can be actually described or explained through these figures. Okay, so for example, you have this permanent magnetics here, and then there's a coil here. So when you push the magnet towards into the coil here, so the coil, a current will be induced, okay, will be induced inside the coil, and then the direction of the current, okay, will create the direction of the current that induced is actually the direction that will create a field that actually oppose the field due to this magnet. For example, this is the field that produced by the magnet, which is not south. So meaning that it is produced like this, right? It's going out. So the current induced is in the direction that will produce a magnetic that oppose to the magnet. So from this example, we can see that this current, the current will be in a counterclockwise direction. Counterclockwise because it want to produce an upward field. Okay, so same again. So when you actually push out this magnet, okay, this magnet, so actually the inducing flux will decrease. Okay, so the coil here will induce a current that will oppose the change of the flux. Okay, so a current will be induced in the direction of what we call clockwise. Okay, so clockwise because it want to produce a field that is actually oppose the direction of the flux decrease. Okay, so that is how actually the Lenz's law stated. So actually Lenz's law only complement the Faraday's law. And another Lenz's law, because actually Lenz's law will have several type of laws. Okay, so this Lenz's law, okay, stated that for a conductor in a closed circuit moving perpendicular to a magnetic field and hence cutting its magnetic field, for example, this one B is the magnetic field is going downward, the direction of the induced current can be determined by using the Fleming's high band rules. And when you have a current, so it will also produce a voltage. So the value of the voltage induced, it can be computed by using these equations. Okay, and this right hand Fleming rules shows the what we call when we have the motion, when we have the direction of the magnet, so we can actually have the direction of the current. Okay, so this is actually also from the Lenz's law. Okay, in a magnetic circuit, okay, we have what we call several what we call losses. Okay, not losses, it's actually what we call the magnetic leakage and fringing. So what is magnetic leakage is actually the flux that not passing through in the magnetic materials or in air gap. Okay, so usually this magnetic leakage occurs at the magnetic source. For example, if you have like this winding here, so we have a flux that is actually surrounding this field, okay, surrounding this winding. So this is what we call the leakage flux. Okay. Another one is the fringing. So fringing is actually what I call a phenomenon that occurs at the air gap. Okay, this looks like a bulge outwards in the air gap. Usually the fringing occurs here. So the type of what I call the flux direction, the flux pattern is actually in the bulge outward from the air gap, and it will actually reduce the flux density. But still, this fringing is still considered as a useful flux as compared to the leakage flux. Okay, leakage flux can be actually regarded as a what we call useless flux because it is actually a leakage. Okay, but for the fringing, is actually we consider as also is considered also as still as a useful flux. So this is the theorem under the magnetism. It's actually we want to go for the magnetic circuit actually. So this is the magnetic circuit. So usually we want to analyze magnetic circuit. Okay, magnet. Okay, we are try to what we call have some analogy to electrical circuit. Okay, so to make the what we call the analysis become easier and so on. So this is a magnetic circuit. So this can be represented as an electrical circuit where we have a voltage source and then the flux as a current and the resistance. Okay. And this is the comparison between magnetic circuit and electrical circuit. So for the current I, so in the magnetic is a flux. The flux density is the current density J. The magnetic field strength is a H, while in the electrical is E. The magnetomotive force is F, and in electrical is also E, which is V. The permeability is mu, and in electrical circuit we have permittivity, which is epsilon, reluctance, and resistance. So this is example of magnetic circuit, series magnetic circuit with air gap. So meaning that you have two type of materials inside this circuit, which is the core, the iron core, okay, and then the second one is the air. So we need to model these two type into a two type of reluctance, okay. And the flux that flow inside this material is the same, okay, for both materials. So as can be seen here, but the reluctance is different, okay, because the reluctance depends on the length of the materials over the permeability of the materials and the cross section of the materials. Okay, so we can write down your core as this one, and the reluctance of the air gap as this one. Okay, and we should know already that we can actually use this, okay, since it's a series, so you can actually use what we call the basic Ohm's law for a series circuit. Okay, so for example, we know that this is V is equal to IR plus IR1 plus IR2. So the same one, which is F flux multiplied with S core plus flux S. gap. Okay, and we can actually write down here, so since it's F, this is Ni, so this one flux Sc plus flux Sg, we can write down as a this one Ni, so Sc plus Sg as shown here. Okay, and we also can actually write down this function as a function. How? So let's look at the relationship. We know that the Ni is equal to the flux multiplied with Sc plus flux multiplied with the Sg. Okay, and we know that flux is actually is actually we know that the B is actually flux over A, right? So the flux is actually BA. So we can write down this one as a BA, and this SC is a length, okay, of the core over mu of the core multiplied with the cross section of the core. Okay, and B, you know already, is actually mu of the core multiplied with H. Okay, so I can remove this and then rewrite this as a mu C Hc. Okay, and then this can be cancelled up, so only left only Hc multiplied with Lc. The same case goes to the Sg. So the flux Sg you can compute by using mu gap H gap, okay, multiply with the air gap multiply with the L gap over mu gap A gap. So cancel out here, so this one also cancel out, that's why we have only Hg and Lg. Okay, so that's why we can also write down the equation as this one or this one. And this is the circuit equivalent when you have what called as several magnetic circuit material and several magnetic materials, which is a composite, meaning that you have some part is iron, some part of it is a steel, and some part of it is a cobalt. So we can actually represent as a series circuit that have a different resistor value. Okay. So the same thing is actually can be done. So you can write down on the equation of this KVL as a this one. Okay, or in other words, also you can write down as a Ni is equal to the flux SA plus SB plus flux SC. Okay, same. And okay, so this is example. So I think we will continue on the next video. Thank you very much.